Another thing that we're going to count in this course is the subsets of a set. Now, if S is a set, then a subset of S is any set contained in S. So for example, let's let S be a 3-element set. So S is the numbers 1, 2, 3. The subsets are the empty set, the set containing just 1, the set containing just 2. I'm not going to bother writing all the curly braces and commas here. The set containing 1 and 2, 1 and 3, 2 and 3, 1, 2 and 3. So there's 1, 2, 3, 4, 5, 6, 7, 8 subsets of 1, 2, 3. Now there's also 8 binary words that have 3 letters. And if I write them side by side, you'll see that it's not a coincidence. We have the word 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, and 1, 1, 1. The correspondence between the subsets and the binary words is that every binary word has ones in some positions. And if we take the positions of the ones, position 1, or position 2, or position 3, and just write the set of positions that holds 1, then we get every possible subset of 1, 2, 3. So here we've got ones in position 1 and 3, and that corresponds to the subset 1, 3 of 1, 2, 3. So this is a bijective correspondence, or a perfect matching, if you like, of the subsets of 1 through 3 and the 3-letter binary words. In fact, this correspondence holds for all n. Turns out there are always 2 to the n subsets of the set 1 through n. The proof is that there are 2 to the n binary words, A1 through AN, so n-letter binary words. For each one, create a subset of 1 through n just by listing the positions of the word which are 1. And this is a perfect matching of binary words. We know there's 2 to the n of them, with subsets of 1 through n. So that's all there is to that. Now subsets also come up when we look at polynomials. It turns out that the coefficients of 1 plus x to the n sum to 2 to the n. The 2 to the n we know is the number of subsets of 1 through n, number of binary words of length n. And again, this is no coincidence. If we think about these things side by side, we'll see why, yes, obviously they all have the same numbers, 2 to the n associated to them. Let me look at this 3 different ways. We'll prove this 3 times. First, let's write 1 plus x to the n as some polynomial in x when we multiply it out. Let's write the coefficients as b0 plus b1x plus b2x squared, etc., up to the highest power is going to be x to the n, bnx to the n. Well, the sum of coefficients is p of 1. If we plug in all ones here, we get b0 plus b1 plus b2, etc., up to b to the n. But if we plug in 1 to p of x, which is defined to be 1 plus x to the n, we get 1 plus 1 to the n, which is 2 to the n. So all of the coefficients have to add up to 2 to the n. So that's one way of looking at it. Now let's look at it another way. Proof 2. Anything to the 0th is 1. So let's rewrite 1 plus x to the n as x to the 0th plus x to the 1st to the n. X to the 0th is 1 and x to the 1st is x. So this is x to the 0th plus x to the 1st times x to the 0th plus x to the 1st, etc., with n factors here. Now when we multiply this out, every monomial in the expansion is something like x to the 0th, x to the 1st, x to the 1st, x to the 0th, etc., depending on which power of x we took from each factor. Now the exponent sequences of each of these monomials are just binary words of length n. And as we know, there are 2 to the n of these. So therefore, 2 to the n monomials, and then when we add them up, the coefficients is just the number of monomials we get. All right, now let's look at it. Oh, sorry, this is proof 2. I want to do a third proof as well. Let's look at this a third way. All right, proof 3. Let's write 1 plus x to the n as 1 plus x times 1 plus x, etc., times 1 plus x n times. Now each monomial in the expansion comes from choosing 1 or x from each factor. So let's let task I be choosing 1 or x from the ith factor. So there's two ways to complete task I. Either you choose the 1 or the x. And I could be anything from 1 to n. So that means the number of monomials equals the number of ways to complete task 1, task 2, etc. up to task n, which is 2 times 2 times 2n times, which is 2 to the n. And the number of monomials is going to be the sum of the coefficients, because when we combine monomials that are the same, that's what increases the coefficient. All right, let's do an example with n equals 3. So we have 1 plus x times 1 plus x times 1 plus x. And we could choose 1s from all the factors, or choose 1x and 2 1s, or choose 2 x's and a single 1. Or choose 3 x's. When we make those choices and multiply them together, we get 1 or x, we get x squared if there's 2 x's, and we get x cubed. And then when we add these together, we get 1 plus there's 3 x's, and then there's 3x squareds, and then there's a single x cubed. Now these monomials we get by multiplying out 1 plus x cubed correspond to binary words. If we think of the 1s as x to the 0 as x to the 0ths, and then write the binary word, we get 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. So a 1 here corresponds to a 0 there, and an x here corresponds to a 1 there. 1, 1, 0, 1, 0, 1, 0, 1, 1, and 1, 1, 1. And then the subsets are empty set 1, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 3. Again, I'm omitting all the curly braces and commas because it's sort of a drag to write out. So we've got various ways of looking at the same thing here. Now there's a nice formula for exactly what the coefficients are. We know the formula for the sum of the coefficients is 2 to the n. there's actually a nice coefficient, there's a nice formula for every single coefficient here. We'll write n over k and put parentheses around the n and the k and call this n choose k. We write this for the coefficient of x to the k in 1 plus x to the n. It's also the number of binary words of length n having k ones, and it's also the number of k element subsets of an n element set. Those are all, this is the name for each of the coefficients, and then these are 2 or 3 different interpretations for exactly what these things are. The formula for these is something we're going to look at very soon. And let me just write that down. So the formula for n choose k is easy, and we'll state it soon. The end.